Okay,
thank you, Brian.
Now it's showing my perception.
That looks okay, I think, Brady. I don't know if Katie's. I don't know enough about Max or anything to say if that will pop back up, but I can just see the slides now.
Perfect. Let's hope that stays that way.
So I think we're just after 6 o'clock now, so I think it's probably a good time to start, if that's okay, Brian.
Yeah.
Okay, so yeah, welcome everybody. Hope you're doing well, and I think welcome back to 2022, and hopefully is this our first event of the year now. So yeah, welcome. Today I'm delighted to be joined by some colleagues of mine here at Oxford Brookes University. We've got Katie, Katie Lukow, have I pronounced that correctly, Katie?
Lukow, close enough.
Lukow, sorry, apologies. And Katie Lukow and Brady Planden, who are going to talk about some of the activities that are going on within the high voltage and energy storage group here at Oxford Brookes. So a little bit about our two speakers, not too much because I know you want to listen to what they've got to say, but both Katie and Brady studied for a mechanical engineering degree in Canada at the University of Victoria, and they've since undertaken a whole range of roles and are active in sort of volunteering regarding promotion of engineering. But Katie is studying for a PhD here at Oxford Brookes University, having previously worked as a mechanical engineer on medical devices, and Brady is a research fellow in the Future Transport Research Group, and also completing a PhD, and previously worked in one role out of quite a few, but as a project engineer at AVL Engine Controls. And more recently has been a project lead for the Oxford Brookes racing team. So I'm delighted to welcome them, and I shall hand over to Brady and Katie.
Awesome, thank you, Dan. So really excited to have this kind of moment to discuss. Sorry, I think if everyone can just mute their microphones and turn their cameras off, I think that would be ideal. So yeah, just really excited to have some time to discuss some of the awesome work that's coming out of our research group at Oxford Brookes University. So my name is Brady Planden, and yeah, like Dan says, we're really excited about the future of transport and kind of battery electric vehicles and all of the fun things that relate to them. So a quick just overview of what we're going to present today, just so everyone can kind of get an understanding of what the schedule is. We're going to do a quick group and school introduction, some lab capabilities for the new HVES lab that we've developed, some overview of the equipment and the specific testing that we can do, and then some of the cool research projects that we have ongoing at the moment. So a step back and discussing a little bit about Oxford Brookes University. So the university is known as a world-class motorsport and automotive university. We have alumni in every Formula One team and most Formula E teams. I think actually now it's every Formula E team, if I'm correct. And we also host the top UK Formula student team that everyone kind of gets involved in at the school level. We're very proud of OBR and everything they accomplish. And then as kind of a specific discussion on the degree side. At the moment, we do MSc in electric vehicles and motorsport as kind of the key international attractions. But as well, we have undergraduate MSc and PhD level degrees. So I guess a thought here for this presentation was kind of giving an overview of where this field is, where it's going, and where we kind of sit inside of it, both at Oxford Brookes University, but also Oxfordshire and the UK as a whole. So what we want to kind of discuss is the next 5 years, the next 10 years, what the current challenges are for electrification, as well, what are some of the successes that we see at the moment. So we think, as a research group, that the next kind of 5 to 10 years will be governed by advancements in ultra-fast charging, longer range for electrified vehicles or any transportation for that matter, a push for a longer lifetime inside of the packs associated in those vehicles or transportation, and as well a huge driving force towards lowering costs for energy storage, specifically lithium-ion energy storage. So a couple cool photos, obviously. We have some racing scooters, we have E-Extreme or Extreme E, then we have some eVTOL. All of these kind of at their basis utilize lithium-ion solutions and are very much driven towards the cutting edge of these solutions. So whether it's improvements in fast charging or longer range, all of these have a direct application of those challenges. And at the moment are still striving to improve or to overcome these challenges to be viable inside of the societal approach. From our perspective, with those challenges, we kind of took a look in maybe fall of 2019, 2018, in that kind of time frame, the pre-COVID time frame, towards what that meant for the school, what that meant for Oxford Brookes University, and we decided to create a research group that was aimed towards solving some of these challenges and providing solutions for energy storage and future transport. I'm happy to say that we are now at 14 researchers. We've got a new lab space and we've got some really, I think, cutting edge and fun projects ongoing. But we've also expanded outside of just the standard postdoc lecture roles and have pulled in a lot of students, both at the MSc and the undergrad level, with the idea to really disseminate a lot of this information to people going into the industry, and to, for new grads that are going to need this skill set that they haven't been able to achieve in previous years, or in previous movements on the combustion side, or whatever the next direction might be. We've also been very happy to get summer interns and are always looking for new interns to come in and support some of the really cool research projects. Distilling the challenges to the group and now into the research themes, the idea for this research group was to come up with some direct themes that we could be kind of working underneath as a group with multiple people in different small areas. And this really boiled down to 3 key areas for us. And that was open source testing methods, high performance pack development, and next generation battery chemistries. So you might have already got a feel for the theme of the school, but motorsport or high power automotive is a huge theme for Oxford Brookes University. And that really distilled into our research aims. We really wanted to make sure that the challenges that we were tackling were challenges that aligned with the students that we have coming to Oxford Brookes, but also some of the areas that are, it's even harder to find solutions for in comparison to standard OEM level. So a couple examples of some of the areas that we are aiming towards and some of the challenges that we want to deliver or solve for the research group in these kind of themes. So you'll see on the open source testing methods, developing open source modeling packages that give you improved information or prediction into lithium-ion solutions. And that might be, continuum level or also down to BMS solutions, so battery management systems, looking at fixture design, data sets, all of these methods that can be shared with a global, a global research group or a global electrification field that improves, this movement forward. On the advanced or on the high performance pack development, we look at sensing methods. So, reducing costs for sensors inside of packs, also improving what sort of sensed parameters we can get out of the next generation packs. As well as you can imagine, thermal management is a problem everywhere you go. Thermodynamics does not change. So that is still there, and we're still actively trying to improve methods. And then on the next generation chemistry, this aligns with fast charging at farther range, looking at anode-free solutions that are lithium metal based, as well as looking at post-mortem analysis so that we can get a better understanding of the microstructure issues. All of this kind of leading towards better cells, better batteries, and an overall better solution for the world. And with that, I will pass it over to Katie to discuss a little bit about the lab.
Perfect. Thanks, Brady. So as Brady kind of mentioned, we have all these great research themes and a lot of this work we're doing. But I guess the big question is, how do we do it? And as Brady mentioned, we were formed in about 2019. That's when we got our first big thermal chamber there. And so we now have a HVES lab on our campus in Wheatley that we're very excited about, with kind of some of our key capabilities being pulse power testing, characterization both at the thermal as well as electrochemical levels, exploratory fast charging, and with that developing custom drive cycle development, which I'll talk a little bit about more, followed by degradation investigations and aging, and then finally stack pressure exploration. So kind of diving one level deeper into that, what does this mean? So in terms of batteries, we can go everywhere from the single cell up to the full pack. So at a cell level, we're looking at around up to 5 volts with up to 480 amps. And with that, some electrochemical impedance spectroscopy, which is a really kind of cool area where we're looking at variable frequency pulses and seeing how the cells react. From there, we can go up to the module level, which you can see the picture right next to it, what we had in our chamber. It's actually currently in our big thermal chamber right now, going up to 1,000 volts and 54 kilowatts. And we do have the capability to shoot EIS there. And then finally, which we're very, very excited about, we're getting a pack tester coming in March, which will be able to do up to 1,200 volts and 330 kilowatts. So looking forward to that. Diving a little deeper, so on the cell level, we have an Arbon system. We can do up to 8 channels, either 60 amps on all 8 channels or up to 480 amps. And with that, we have our Gamma-ray potentiostat that interfaces there. At the module level, we have an ETPS power supply. It's quite a beast. It's very large. And this is one that's doing 54 kilowatts. That we can also do battery emulation, or it can act as a module tester. So we can kind of go both directions with that if we want to do some motor and inverter testing. And then finally, as I mentioned, our pack tester that's coming in. Unfortunately, due to some chip shortages, I'm sure we're all feeling that has been delayed, but we can't wait to start testing with this and getting some of this really high power, high performance applications in our lab. We do perform all of our tests in environmental chambers, kind of for 2 reasons, both so that we can test at variable temperatures, as well as just to kind of ensure we're in a controlled environment. So our top one here is 800 liters. It's bomb-proof, it's explosion-proof. It's what we use for our modules and some small packs. And then we just have some smaller binder chambers that we use for all our cell level stuff. In addition to that, we do some embedded development and some BMS development on the software side, using everything from MATLAB to Simulink and Julia, and then deploying that with ETOS, and then using Inca and Canoe, and the hardware along with that being an ETS rapid prototype unit, as well as the vector unit. So that's kind of a quick overview of everything, kind of where we do it. But I think what we're most excited to talk about is definitely our research projects and some of the work we have going on. So I'm going to start it off with our battery testing consortium. So as a trend here, we know that electrification is definitely the way of the future. And alongside that, we're seeing the Formula student teams all tending towards that. And when the Oxford Brookes team went electric in 2018, we noticed there was a big gap in knowledge across the board and kind of deciding what cells they should use and what's the best way to design a pack. So we've come up with our battery testing consortium. And what we're really aiming to do is open up this data and open up this characterization information to provide these teams insight into battery management calibration, into proper design, thermal management, all that kind of stuff. So kind of taking them from this cell level decisions right up into the pack. Some cool things that we're aiming to look at here. So this is called a Raygon plot, and we're looking at energy density and power density. Now, ideally, as Brady kind of alluded to when we're looking at these new cell chemistries, we would be as high up in that right-hand corner as possible. However, we're not quite there yet. So when we were selecting cells for this, being a formula student situation, we really wanted to look at these high power cells. So you can see the majority of our cells are tending towards that power density. However, that comes with trade-offs. Comes with trade-offs, mainly being cost. So we have thrown in some cylindrical cells. So the triangular cells on this plot are a cylindrical cell, so similar to what you'd imagine a AA form factor would be. They're cheap to make, they're cheap to acquire. However, are more difficult to package, as well as you get some issues there with the circulars being a pouch cell. Just want to shout out really quickly, we do host all of our open source projects on GitHub. So you can see, and you'll see it a lot in this presentation, on Oxford Brookes /HVES, you'll be able to find some of our open source BTC data, as well as some of the projects Brady's talking about later on. So definitely take a look and reach out. So taking that Raygon plot data, kind of where do we go from there? So as part of our testing, we want to make sure that the cells we choose are viable in a pack configuration. So we've gone in and designed a pack for approximately 600 volts. And you can kind of see here what that looks like. And something that's interesting to point out, I'm going to jump back and forth here really quick, is if you look kind of in this bottom corner, we have molasta number 4 and molasta number 3 that are really these high power density cells. However, when we start considering all these other things, such as pack efficiency, which is how this plot is sorted, and thermal heat rejection and math, they aren't actually necessarily the best cells to choose. So it's really important that we consider all of these different options. A big one that we're seeing as we kind of talk to some of these teams is that thermal heat rejection value, where while you might have some benefits with the cylindricals, you have to design a much more complex cooling solution as you have a higher internal resistance, and you end up rejecting so much more heat, of course, which is correlated to our pack efficiency. So kind of, we have all this data, what can we do with it? So as I mentioned initially, a big one is helping us create this better battery management system. So being able to get really accurate open circuit voltages from it, as well as kind of getting an idea of how is our cell going to react. So you can see on the right-hand side, apologies. We have some numbers where we've tested at everywhere from 5 degrees C to 45 degrees C at different discharge rates. And you can see the cell really wants to be at 25 degrees C. Of course, if everyone was, I think it was 2 years ago, we had that huge heat wave when the teams were out running, and they're actually going to be running at 35 to 40 C. So they need to know how their cells are going to react and how they can account for that. And then additionally, giving this ability to compare. So one of the really exciting things that we have the ability to do is, as I alluded to earlier, is create these custom drive cycles. So we've gone in using a lap simulator and taken one of their tracks, put it in, and then we run these cells through it. So the very first plot you can see here on the left, we are comparing 2 different pack configurations. So if we have a 450 volt pack versus a 600, how is it going to perform? And you can see the 450, it doesn't actually finish. And then in the middle, taking a look at 3 different cells and slightly different chemistries. And you can see if you're a team that's maybe looking to keep your cells for more than 1 season, you actually can't really go with some of these cells because they're going to degrade much faster. And then finally, the resistance growth, which again, going back to this cooling solution, if you're designing your pack and you're kind of working towards this thing when your cell is new, knowing how that's going to change over its life and how you need to account for that can be invaluable. And then alongside this, one kind of smaller project that we really want to bring up is our pressure fixture. So one of the key issues with pouch cells, while providing maybe better energy, better power density, they need a face pressure. So you need to apply pressure on either side. And when we're doing this data, we want to make sure that it really is as accurate to what they're going to be running in the car. Otherwise, it's not super useful. So we've gone and we've designed a modular fixture that we're able to use, I think, for 8 of the 9 cells, so that we can kind of minimize the cost across the board and make sure that we're giving the most accurate data we can, and the most repeatable data. So we have pressure sensing integrated into this. We have thermocouple and temperature sensing integrated into it, to really ensure that we're providing kind of the best and most repeatable data we can, not just for the BTC, but across the board when we're doing these tests. So that wraps up the first one, and I'll hand it over to Brady to dive a little bit more into the modeling side of things.
Perfect. Okay, so now that we've kind of went through the experimental acquisition, another perspective we have inside of the HVES group is electrochemical modeling. So one of the projects that we're currently working on and we're really excited to deliver is called LIBRA. So it's lithium-ion battery realization algorithms. So the goal of this project is to take a model that represents a cell at a continuum level where there's a lot of these partial differential equations that are quite expensive and complex to both validate and computationally solve, and reduce them to something that we are able to solve quite quickly and deploy onto battery management systems that would sit in your vehicle, your scooter, and possibly in the planes as well. So one of the solutions we go about doing this is taking these continuum order models and essentially doing an impulse response or a derivation towards a discrete time realization. So you can see that some of these are gradient based. So there's additional partial order differentials for diffusion that are kinetically driven. And what we result in is a response that's a function of the input current, and not as a third or fourth order differential equation. So we can move forward and deploy those type of controls through LIBRA. And this is a open source package that we've developed and are currently hosting on GitHub. An overview of how this package has been developed is on the left here, where we can kind of get an understanding of some initial cell definitions. You want to pick a method that you would use, and then you essentially iterate through this package of generating realization transfer functions, and then finally you result in a bunch of small arrays, so mathematical matrices that you would multiply together, and that would give you a final response of the system that you could validate off of a continuum order model, as well as some additional reduced models. One of the things that we're quite excited about with this package is the use of Julia, which is an, I would say, up-and-coming modeling language. It was originally developed out of MIT about, say, maybe 9 years ago, with some really cool direction towards performance, multiple dispatch, as well as a dynamic typeset. So it's very similar to using MATLAB, but with a multiple order kind of increase in performance. So I guess all of that being said, what do we really get out of this? What is the idea or the need here? You can imagine that a BMS is only as good as the information it has. So you could, you're essentially trying to control the pack. You're wanting to make sure it stays within safe hardware limits and still provides the power and the range that the client wants, or the driver. So really what we want to improve is the information that BMS can receive without adding a bunch of additional sensors or expensive solutions that would have to be added to each pack, and OEMs would have to investigate or possibly have failure rates associated with those sensors. So we can do this mathematically, and what we can do is deploy these mathematical models onto the embedded controller, and then gain that insight without having to add 20 sensors per pack. Some quick things to point out here: we can essentially simulate. This is just a pulse discharge for 10 seconds. So this is essentially being discharged here. There's a rest for 40 seconds on the cell, and then a pulse charge for the same 10 seconds with that 40-second rest being followed. And the resulting internal concentrations can be viewed inside of this model. So this is the electrolyte concentrations as a function of where inside of the cell you are, as well as the electrode concentrations, both at the current collector and at the separator interface. So this is the negative electrode current concentrations, positive electrode concentration, and then I didn't show it because you can get a lot of information from these models, but the associated potentials are also available there. So you can couple degradation models into this as well. So you can start predicting what the cycle lifetime of the cell or the pack will be under a given drive cycle that you might be experiencing at the moment. So it's something that can be done in real time. Some cool results off of this. This is, we're actually really quite excited about this. We've done some comparisons between some other modeling methods and different, I guess, targets for this package. Inside of an Apple MacBook Pro with an Intel CPU, we've compared a MATLAB implementation with a Julia implementation, which is Libra, as well as Libra on an ARM solution, which is a smartphone. So we have a Snapdragon 865. We were able to get a Linux OS running on it quite easily. And then we added Julia to that, and we wanted to see how fast we could create these models to get an understanding of if this would be possible in vehicle, so that you could have your car updating, an over-the-air update, triggering a new model generation, at 10 p.m. one night, and there would be that possibility to have new models before the next morning. And the answer to that is absolutely, and you don't even have to wait that long. So we found a 2.57 mean across these whole operating ranges in terms of improvement over the MATLAB implementation. So essentially, just a quick overview of what I'm showing here. This Hankel size is essentially how much of the response time do we actually use to calculate these arrays. So we might take those continuum models and create these small impulse responses, and we might set the total array size might be a time series for multiple hours. So that, with the really slow dynamics, maybe the concentration diffusion is still moving after 4 hours. So we get all of that information, and then this Hankel size essentially is how much of it do we take. So a Hankel size of 2,000 might be we take the first 30 minutes of data, and then the Hankel size of 4,000 might be we take an hour's worth of data, just as an example, not an actual implementation for this. But this is kind of a good indication of some of the performance of the final model. But we can see that even at a Hankel size of 2,000, which actually gives us a pretty good model, it's going to take 12 seconds per state of charge implementation. So a total model that's running on a Tesla infotainment system might end up taking on the order of 5 minutes to complete, in comparison to the full night or something even longer. And we actually see that after a Hankel size of 2,000, it's faster to run Libra on our old smartphone than it is to run it through MATLAB on our MacBook Pros, which is a really cool insight that we're really happy about. A final project, just to kind of wrap us up here. One of the additional areas that we're very interested in is thermal characterization and thermal modeling of cells. So an issue that we initially found was we wanted to generate thermal data cheaply or very quickly. And one of the current standards to do this is through accelerating rate calorimetry, which has a very, very accurate method, but it is also quite expensive and does use up a lot of space. So one of the things we wanted to investigate was whether or not we could do that internally for a lower rate, with some acceptance on maybe not getting the same data fidelity out of the final solution. So we wanted to look at capturing bulk specific heat capacity, as well as internal thermal conductivity and external as well, to be honest. So we've generated this thermal fixture that allows us to investigate this solution or this methodology we've created, all 3D printed with these very cool fans that allow us to vary the essentially the thermal contact value of the cell, and then we run it through this this pulse train effect to charge discharge the cell really quickly, back and forth for a long period of time, essentially giving us a joule heating input into the cell due to the internal resistance we get. And that will give us, over time, a quasi-steady state solution. And by changing the fans, by turning them off and on, what we can do is essentially create a algebraic solution where we have, I think it's 3 unknowns and 3 equations. So we can perfectly solve for the final solution for this thermodynamic system, as well as gain some of these insights that we've been looking for, that we can get out of a traditional calorimeter, but we can do cheaper, possibly quicker. But I will say that there is some associated error once you get down to further decimal points. So there, and different operating conditions, to be honest. But it is a really cool outcome, because it is really expensive at certain times to do full characterization on thermal characterization for cells, and we want to be able to offer that to clients or research partners, collaborators at a lower rate initially, and that can give you some insight into ballpark areas for thermal design of a pack or thermal cooling, without having to spend the total sum towards getting really high quality data. And I will just end there. I'd love to thank everyone for coming out and listening. All of our information is right here, and really happy to take any questions.
Thank you, Brady. Really, and Katie, a fascinating insight into what's going on in the world of electrification, I think. So I guess opening up to the floor, if people wish to ask any questions of the speakers. I don't know if you're able to put them in the chat, are you? Please fire away if you've got questions.
There's no stupid questions.
Any questions that people wish to ask? We've got some coming in there. So there's one there, I think, that is the bottom's dropped off. Oh, there we go. What is the biggest challenge to rolling out electric vehicles in the domestic sense across the UK, both technology related or commercially?
That's a good one.
The $1 million question.
Yeah, definitely. I think at the moment it's mostly policy. That would be my perspective, and Katie might have a different one. Global, like the UK, is in an interesting position because I think as a whole we're actually a bit smaller of an island than some of the difficulties we might see, for Katie and I in Canada, or even moving into the US, South America, those markets, or even maybe Russia and the Middle East Asia. So the UK, we are in a good position to be able to cover the UK for charging solutions, as well as the commute distance for the average person. The population density is quite decent, so I think policy towards getting further charging infrastructure, or at very least informing people of the current charging infrastructure and getting that out into society would really benefit a lot of people's anxiety towards going towards an electric car for their next purchase. I do think that at the moment the offerings we have are quite limited in terms of selection for an estate car that you don't really have too many options at the moment. There's the M5 from MG, that's a state, but there isn't too many other options for people to get out and, they have a preference for their vehicle and they want to purchase that. But also the costs aren't crazy low either. So I think, the vast majority of the UK maybe isn't spending £30,000 on a car or £40,000 for a Tesla. They might be looking at a used vehicle in the £15,000 to £20,000 range or even lower. And there aren't a lot of solutions there at the moment. So I think a lot of people are still looking at, okay, maybe PHEV will be my next vehicle, not a full electric solution. And it's just kind of getting those vehicles to that community. It will be a challenge for sure.
Yeah, I'd echo a lot of what Brady said, but I think also improvements in fast charging and ultra fast charging are a big issue. Currently, it does exist to some regard, but it's kind of at what cost? And it's kind of limited to these high quality Taycans and Model S's. And in all honesty, I think people want to be able to do it. They do it at the petrol station, go in 5 minutes, fill up and leave. Particularly around kind of when you're on a road trip, you kind of want to be able to go in and grab your coffee and be fully charged. So I think that's the only other one. And then, just with infrastructure, it seems that a lot of people say every time they go to a charging station, 4 of them are broken and 1 of them is working. But that definitely needs to kind of come at that top level. I mean, we're in Headington and Oxford, and there's been new chargers there that have been there for 3 months now, but still aren't up and running. Mm-hmm. So just really having that push through is really important.
Mm-hmm. I will say that we speak from a perspective of, I guess, not the brightest days, but actually in real life, when, if we were having this discussion 3 years ago, we would be saying there's the Renault Zoe or a Tesla, and that those are your options. But really, when we start looking at what's available at the moment, even in terms of fast charging, we look at the Hyundai Ioniq 5, where you can do 20% to 80% in 18 minutes or something like that. If you start looking at that perspective, we're getting close. We're getting there. Yeah. It's just maybe the technology needs to move a bit and policy needs to move a lot.
Yeah, I will say it is really exciting to be in the UK. We were back visiting our family this year, and my parents are kind of looking to buy a new car, and they have either like a car that's going to cost them $100,000 or a car that's going to cost them $60,000 and still not great. So it's really exciting to be here and have, albeit it might feel small, but quite a few options. Cool. There's a lot of questions, so we should probably move on.
Okay.
I think, no, it's a good point. I think it's multifaceted aspect, isn't it? The rollout. So another question: Have cells been tested for immersion in seawater?
Seawater immersion. Yeah, that is a good question. I think the easy solution that OEMs are going with at the moment are ISO standards or equivalent standards for the pack level. So you just remove any sort of humidity from the cell level, where you will have tabs and bus bar connections, and avoid any of the issues with corrosion inside of the pack by just sealing off the pack and ensuring that no humidity or salts would penetrate it. Some really cool videos at the moment around the Rivian truck that's going through hugely submerged water. Tesla's going through hugely submerged water. I think actually what we end up with was electric vehicles that can do more submersion than a standard combustion vehicle. But that's a really good point around salt water and ensuring that the
corrosion,
there wouldn't be a corrosion perspective. I assume most of the OEMs are actively solving that problem, but we haven't done any work in that area.
The part of the question, if you can hear me, was about fast discharge of a fully charged battery due to seawater.
Oh, so like a short, essentially, or completing the current circuit through.
Absolutely. If it was in a boat or it was a car that was left on the beach and the tide comes in.
Yeah, definitely. So we've had, I guess, most of the lithium-ion design ends up with these containers that have been encompassed or enclosed to avoid any sort of penetration of any liquid, to avoid exactly the point you're bringing up, a possible current path through the tabs via the salt water or any sort of water, I guess. I suspect most of the OEM, or not OEMs, but the lithium-ion solutions for boats will have that O-ring seal or whatever it is. But you're right. If that was removed and or you're working on the pack at that point and it was submerged, you could run into a thermal runaway event
really easily.
Yeah, luckily maybe you have the cooling around you anyway. If it's submerged, the pack will be cooled by the seawater. But if not, and it's just like a tide coming over, shorting briefly, you could damage the pack for sure.
Yeah, there's currently some bids open in Europe looking specifically at kind of how do we electrify these large boats. I think that one's like at cruise ships or something. But it's definitely a really unique challenge.
Thanks for that. Hopefully it answers some of that, Mike. Big sort of challenge, I guess.
Yeah.
I think we've got one. What is the likely energy density that could be achieved in the next 20 years?
That's a good one. I was just reading there's a lot of literature at the moment, and I think, just there is an issue with the battery community around distilling or disseminating a lot of this information. And I think, just why I have an opportunity, I think there is a lot of ill will with the media around these next generation achievements. I think it's very common to see a Nature publication or a publication in the Journal of Electrochemical Society to then be caught by some media journalist or a media conglomerate and then be modified to sell something that it actually isn't showcasing. And I think society ends up seeing these posts and going, oh, it's just another battery breakthrough. Call me when it's out of the lab and it's actually being deployed. And I do think a lot of the research, the academic research, isn't around, okay, this is a solution immediately, but it's that stepping stone to getting something that will be, in 5 to 10 years at 1,000 watt hours per kilogram. To answer your question specifically, I think within the next 5 years, we'll be seeing over 500 watt hours per kilogram, specifically towards solid state batteries, as well as liquid electrolyte with lithium metal. But Katie, what were you thinking?
I guess I would definitely agree with that. I do think that we'll start seeing some diminishing returns with it as cost is driven up. That's definitely one thing I see kind of in the transition into industry. People care most about cost. And so I think we'll see we're seeing some lithium metal cells right now that are in the 450 to 500 range. And I think I wouldn't be surprised if we kind of start peaking at that. And it's like, okay, now we have something that's acceptable and maybe comparable to an energy density we might see in a traditional combustion sense. How do we now lower that cost? Or how do we now work on extending that range? I think energy density is one of kind of the easiest ones to pick up on and is really exciting. But it's definitely, there's a certain point where you don't really care if your pack gets lighter. You now start caring about all these other aspects of how much is it going to cost me? How long is the cell going to last? What are the environmental implications towards the materials that I'm using to get this energy density?
I guess to bottle that all up into something that answers the question, 5 years, looking towards over 500 watt hours per kilogram, 10 to 15 and 20 years out, I suspect we'll be in different chemistries for the cathode side, towards outside of NMC, possibly looking towards sulfur cells, lithium air cells in 20 years possibly, and then that's 1,000 watt hours per kilogram. I would start thinking the target becomes. But lifetime becomes a big issue in those areas.
I don't foresee it really pushing past 1,000. I foresee that kind of being a target, but I mean, Who knows?
I'm sure if
Yeah.
this was asked in the 1940s around the
Yeah.
combustion engine, there would be similar thoughts.
This is true.
Well, yeah, certainly it'd be an interesting journey for everyone on it.
Mm-hmm.
Sure. What was the next one? I'm losing my place. But yeah, how optimistic are you that battery capacity and life can be improved by an order of magnitude from today's values? Maybe that links to what you've already said, but
Yeah.
So battery, go on.
In terms of life, I'm confident. I think there's a lot of, not just in like cell development, but in the way that we treat these cells. So I was looking ahead, and there was a question that was a little bit alluding to like things like depth of discharge. So what are we cycling these cells to? How are we packaging these cells? What kind of temperatures are we storing them at? That there are already a lot of improvements that are being made actively. I mean, you see like this 1,000,000-mile battery posted a lot. That I do think we'll see it improve to an order of magnitude.
Yeah, I absolutely agree. I mean, capacity can scale quite heavily. I mean, even at the moment, we can generate really large cells, in the order of 100 amp hours or even higher. I think it for the lifetime, it always comes back down to the cost associated with these changes. We're already at the spot where you can get cells that their lifetime is, for all intensive purposes, forever. By the time the car will be fully degraded by the time the pack is degraded. And this is looking at, you start seeing over 5,000 cycles and still at 90% state of health. But the flip side is usually there's some additional constraint with those packages, whether it's a little bit lower energy density but it lasts forever, or the cost is very high per cell. I'm still very optimistic that we'll be able to get cells that have high energy density, power density, that will hit 1,500 cycles, 2,000 cycles, which is the equivalent of, I don't know, 1,500 miles, or sorry, 150,000 miles, 200,000 miles. We do see, even in Teslas at the moment, there is some data showing battery lifetimes that are extremely promising when properly cycled in climates that make sense. And then you start seeing actually the degradation isn't a huge effect. It's the car, being degraded first.
Yeah.
Yeah, certainly with all the salt in the UK, my car certainly doesn't like.
Yeah, of course.
So I think we've got one question about Fire Industry Association. They're wrestling with recommended suitable fire protection when things go wrong. Do you compare different cells, and what do you recommend? Probably not. Fire safety is probably not something you've.
I think it's so cool. I think it's really exciting. It is definitely a major consideration, and it's something that we deal with the Formula student team a fair bit. However, kind of stepping back from that, that is one of the major hangups with some of these new chemical compositions. So I believe, is it silicone or is it the lithium sulfur cells or lithium silicon? I can never remember. There's what I can't remember off the top of my head. But there is one type of chemistry that's kind of been floating around, but is extremely volatile, and can be a major issue that if you get any kind of puncture, and most cells, to be honest, will immediately light up. I mean, it's kind of a big reason why things like LFP cells, lithium iron phosphate, are used so frequently, because they last forever and they're incredibly safe. However, it comes with these limitations. As we start pushing these boundaries and looking at new chemistries, there's all these new issues that we're coming across.
Yeah, definitely. It is a really cool part of the field. Like Katie's saying, I think we're always trying to push energy densities higher. Luckily, that doesn't always go hand in hand with thermal runaway events. So I guess lithium sulfur cells, wasn't the one you were
No.
you're thinking of.
That's not what I'm thinking
So,
of.
for example, lithium sulfur cells do have very, very high stability, but a lot of issues that first need to be sorted before they can be deployed worldwide. But we do kind of, I think the field as a whole is looking towards the exchange of thermally stable cells and still accomplishing the energy densities that you need, to microscale and across all the scales of the cell.
So that doesn't really answer the question. That's mainly me just getting really excited about battery safety.
Yeah.
There are definitely, though, like looking at different cells, there's definitely that comparison and stabilization. But it's more of a how can we minimize that risk without compromising the performance of the vehicle, whether it's better packaging methods or better BMS solutions that are going to control our operating factors to kind of prevent that thermal runaway as best as we can.
Yeah. There, in addition, there is some research going around pack design specifically to encompass any thermal runaway event or to minimize it in the event that it happens. And that's looking at new materials, but also adding in barriers, internal structure into the pack to avoid one cell having a knock-on effect on multiple cells in a module and then into the pack. So if you can stop it at a single cell level, the rest of the pack is salvageable, but also you don't run into these huge fire events. And specifically when you look at transportation that can't have fires because of safety limits, aircraft, passenger aircraft for sure, or any sort of light rail tube systems, that's where they start adding it. It doesn't matter what the mass association is. Passenger aircraft is a little bit different, but they need to make sure that that safety is there.
Something like railway, which there is a question kind of coming up next, that's definitely something that you might trade off. We're going to trade off the mass, we're going to trade off the energy density to ensure that should something happen, we're keeping our workers and we're keeping everyone safe.
Yeah, big sounds like big area to be involved in. I think the next question was on predictions for increased battery life, but I think sort of answered some.
Yeah.
Is there anything else you wanted to add on predictions for increased battery life in the next 10 years, say?
I don't think so. I think we covered it pretty.
Okay.
Talk to me in 3 years when I'm done my PhD. Hopefully I'll have some better answers.
Yeah, there's one related to railways here. So talking about batteries becoming more powerful, enhanced battery sort of management systems. Do you think charge cycles for large train size batteries can be brought down to below 15 minutes?
Yes, absolutely. We had a bid about this time last year, and it was a Faraday Challenge bid that was associated with heavy duty industry hybrid electric vehicles. So this, I guess, it's a little bit of a roundabout way to answer your question, but this specific application was for mining trucks and looking at mining truck solutions for essentially a hybrid electric setup. And the idea here was we need to maximize the available time to do fast chargings in these specific applications. So there was some really cool chemistry, and we were working at it with a company in Cambridge that had a really cool anode solution that allowed you could do fast charging in something like I think it was 6 minutes or 6 to 12 minutes. So it was absolutely possible.
Yeah, I think the big one there is still kind of going through that stepping stone of maybe looking at a hybrid solution first. So maybe we're not jumping to fully electric right away. Maybe we're looking at doing a diesel electric hybrid or something of similar to kind of help offset that issue. But I think especially if you look at things like light rail transit, a lot of it is going fully electric. I believe in Vancouver, British Columbia, their light rail is fully electric based off of hydro, so it is very clean. So there's kind of that first stepping stone's definitely already there. Is how do we kind of go to that next step?
Yeah, ultra fast charging is absolutely one of the highest priorities that I see from the academic side in terms of what does electrification need to solve to be a viable solution in so many of these transportation areas. And I think at the exchange of energy density, there are solutions that give you ultra fast charging in these areas.
No, fascinating. Our obsession with time, I guess. And,
yeah, I mean, when you're looking at commercial, every minute you're charging is a minute you're not making money. Is the unfortunate trade-off there. So it's definitely very critical of things like definitely in Canada, kind of in these commercial trains that are taking goods halfway across the world. It feels like that downtime is really critical to minimize.
Right, and if you look at the UK perspective, if we have to wait for a train to show up at a stop and it's late, yeah.
Oh boy.
Yeah.
Yeah. Whole new world. Is it likely that battery solutions will continue to dominate the market out to 2050, or will hydrogen electric become a more effective solution?
Man, if I had the answer for that, I feel like I'd be able to start. I could be a politician, I'm sure. In all seriousness, I think it's really, really hard to make predictions that far. I suspect that there'll be a mixture for a lot of the transportation sector. So high power or high heavy industrial solutions will probably tend towards hydrogen. With the consumer level, probably tending towards battery electric. I think the main reason that I have that perspective is just the scale at which it's being unveiled at the moment, or the scale at which electrification is happening. Consumers, I feel like, and this is, everyone will have a different perspective. And, if we toss the coin and waited until 2050, some of us might be right, some of us might be wrong. But I have this perspective or the thought process that once people move across to an electric solution, they won't want to deal with switching back to a hydrogen solution. It is probably extremely beneficial to be able to charge overnight, and that infrastructure will be invested by 2050 to be able to plug in overnight and always have a full car, never having to stop at the petrol station and sort with that, never having to pay the petrol costs and associated maintenance with petrol vehicles, because I suspect that'll be a very fast motivator for people. Obviously, this doesn't necessarily compared to hydrogen, depending on the type of hydrogen. But the issue of filling will still be have the same perspective. And I think a lot of the time it's just what's the first to market. When you start looking at long scales like 2050, though, I do absolutely see that these heavy duty solutions will be driven off of larger scales. Perhaps by then our electric grid will be more green, and the direction towards generating hydrogen will be more green as well. And it's just kind of thinking about what sort of policy will be put in towards climate change as well, and perhaps that'll have a driving effect on these solutions.
Yeah,
it's fascinating. I think is it Volvo are already producing heavy goods vehicles that are battery electric up to 20-something ton. I might be wrong, but
yeah.
And they're also involved in fuel cell technology as well for larger vehicles.
Yeah, I think when it comes to heavy duty, I think you'll almost always kind of a hybrid solution is always going to get you what you want. There's never going to be one catch-all. And so, but in terms of consumer vehicle levels, the infrastructure cost to implement hydrogen is just so high, and the safety implications with it, I think will drive consumers away from hydrogen. However, when you start looking at these heavy scale, even if you look at things like buses and lorries, I wouldn't be surprised if we see kind of some of these hybrid solutions driving in that direction.
Yeah, definitely a mixed approach, I guess. So there's one that yeah, we've got an interesting question. I don't know whether there's a real answer or an answer that you can give here, but it relates to the environmental damage and dangerous working practices associated with mining in poor countries. What's being done about this? Maybe there's, yeah, the whole advancement of technology, maybe as highlighted here, has a cost associated with it.
Yeah.
Maybe that's not something that's in your current remit, to be fair. So
it's not necessarily in our current remit, but it's definitely a very well-known issue within kind of this whole battery space. And there is, I think, another really big part of it with the climate issue is there's a large focus on how can we reuse these materials and how can we kind of minimize that mining requirement. So when these cells are getting to the end of life, can we pull out that lithium? Can we pull out that cobalt and reuse it? Because it is a finite resource like anything else on the planet. Unfortunately, I don't think I have much more to say on that, but it is a very real issue that we can't ignore. Do you have anything else to add?
Yeah, just that I fully agree that this is a concern that needs to be associated or put into policy for the countries that are, you know, driving the OEMs towards or any high level user of lithium-ion cells. There should absolutely be a policy in place on clean and sustainable generation of these cells or manufacture of these cells. Like Katie's saying, recycling is an absolutely amazing method towards minimizing some of that impact on the earth. I think there's a lot that needs to be done. It's outside of our research for sure to be investigating, but I think in a similar perspective, we as a society need to take a look at, you know, there's never going to be a silver bullet. There's always going to be some sort of damage that's being done. How do we minimize that? So what solution gives us the minimal impact towards climate change, towards you know, driving
personal impact is maybe the best way to say it.
Personal impact, yeah, exactly.
And that is kind of alongside all of that, that is part of this underlying issue of how do we make cells last longer? How do we use less cells by increasing this energy density? And there is a massive push of how do we use less cobalt? Lithium's kind of this high level, it's a lithium-ion battery, but it's often the cobalt that's actually the issue. So how can we move away from these cobalt-rich cells and implement with things like nickel that are a lot easier to come by, a lot cheaper, a lot more ethical to mine? And kind of move towards these other methods. Yeah. I hope that answers their question.
Yeah, definitely. Thank you. It's a difficult one, and I guess it's not solely sort of electric vehicle development. It stems across many aspects of society and manufacturing.
Absolutely. And it's like petrol's not without, like, no matter what we're using as our energy source, there are massive implications. And it's kind of looking at how do we minimize this and how do we support these communities that are doing the actual work.
Yeah, absolutely.
Perfect.
Fashion to transport, I guess, and many things in between. So thanks for that. There was something about here. Are there any common methods for dealing with thermal cell rupture or physical cell rupture? Might be outside of the scope.
Letting it burn. Unfortunately, there's in terms of kind of the work we do, there isn't much we can do if we see a thermal runaway event. Kind of ensure that it's safely away from everyone else. And remove it from the situation and remove yourself from the situation and let it burn itself.
Yeah, and I think for like we have the perspective of like an experimental
area,
laboratory. So we deal with single cells or varying cells and probably interact with them much more than, well, I'm 100% sure, much more than anyone would that just buys an electric car.
Please don't go taking your pack apart.
Yeah, definitely. But I think in terms of common methods inside of the industry, first most cylindrical cells give you that extra barrier towards rupture that you would get over a pouch cell to begin with, and that absolutely is one of the driving reasons towards using cylindrical cells. Plus, they have a vent solution that a pouch cell won't have. So you gain some safety benefits towards using just selecting the proper geometry for your application, as well as looking at maybe even some benefits in cell-to-cell variations with cylindricals versus a pouch solution. Inside of that, there's a decent amount of literature around doing pack design specifically towards minimizing cell-to-cell effects from thermal runaway, or developing solutions that can adequately cool the cells. Like Katie's saying, once you've got into a runaway event, unless you've designed for that to happen, and that's probably what the question is. What are the common methods? Looking at barriers inside, so internal pack structure, like we were talking about, is a solution for that. It's not easy, absolutely, yeah.
I think from our perspective, the current method is definitely trying to design to prevent it to happen. So ensuring that you kind of have these safe operating limits, ensuring that it is kind of in an enclosed facility. So if we're testing kind of a module that I showed earlier with a BMS, ensuring that the module is isolated. So if something does happen, you're not burning down your BMS or anything else, and kind of just dealing with it as safely as possible and minimizing the damage to anything else.
Yeah. Fantastic, thank you. Then there's a question about your some of the figures you showed actually, regarding the degradation figures. Were they taken after full capacity cycles or 20% to 80%, for example?
Yeah, so for this cycling, because it's with the Formula Student Database, what we've done is we've cycled kind of through our endurance cycle a handful of times, so we don't actually necessarily get 100 to 0 each time. But then when we take the capacity, we are taking it from 100 all the way down to 0 as state of charge.
Yeah.
Because as their usable energy, because that is kind of what they're pushing their packs to do.
Yeah. Yeah, so it's not an 80-20 cycle as much as it is a drive cycle degradation. So it would be the same. What we are trying to do with it is give a better perspective on how these cells will react under the dynamic operating of a Formula Student vehicle, because that's kind of what the database is driven off of. So it'd be the same as using like a WLTP or the World Harmonized Drive Cycle for degradation investigations of a normal vehicle, and not just doing static cycling. So that was the idea there.
That being said, there's some incredibly interesting research being done that we're dabbling in, as well as some of the other groups within the UK, about how depth of discharge affects the degradation, and kind of looking at maybe an asymmetric charge discharge profile and how all of this stuff can affect the life of your cell. So it is some really exciting work that we're looking forward to investigating more, and that's being done across the board and within the industry.
Mm-hmm.
Lot to investigate here, a lot of challenges.
Yeah.
Which are the most promising batteries for static service in the balancing of the electricity grid? If there's anything you can say on that.
Yeah. Probably the cheapest and longest lasting cells. I think at the moment a lot of them are lithium iron phosphate cells. There is a lot of work looking at second life applications, and there's a lot of challenges that go into that. We have a PhD student in the group that's looking at second life applications and how that would interact with the grid. I think at the moment the vast majority, I don't know, maybe not vast majority, but a large percentage look at lithium iron phosphate solutions because they have extremely long cycle lives, as well as they're thermally stable and really have a good response towards thermal runaway issues or anything like that, as well as they are very cheap. So I think it's cost and lifetime for the vast majority of the grid providers, because I do think that as much as myself at least looks at the grid as we need to be moving towards something green for the sake of the world, I think a lot of the grid providers look at it as what is the cheapest solution towards providing our remit for the year. So I think that to get that into a position where it's actively being used is we have to check these boxes so that the providers will move forward, or policy needs to be driven off of that.
I think, again, the kind of the one thing you have going for you when looking at that area is you're not trying to move anything. So your energy density becomes a lot less critical, and oftentimes you can maybe make it a little bit bigger to get these things like a lower cost or maybe a safer solution. And right now there's no competing with LFP because it's so cheap and so easy to make. But hopefully going forward, we might see some better solutions, because it all ties back into things like the climate change impact and all of this of, okay, well, now we need 2,000 cells instead of 1,500 cells, and what's the implications in the materials required for that, and all these kind of things.
Okay, so again another another balancing act in a sense to deal with.
It's a big trend currently in the battery community of this and problem. Everyone wants a catch-all that's cheap, energy dense, power dense, ethical, commercially available, and there isn't a solution right now. So you're kind of playing this balancing act of what's most important for my application. Because if we toss it the other direction, we look at eVTOL, it's the exact opposite of we're now trying to lift something into the sky, and energy density is so important that we're probably not caring about cost because we just want to get something.
Yeah. It's,
batteries are definitely it's a compromise on so many fronts. And then it's really difficult because the compromise is at the system level, but you modify things at the micro scale level. So you have multiple, size levels or scales to go up until you see your final solution. So, just getting something, a small change at a microstructure that looks very promising, by the time you get up to cell level and pack level can result in a wrong direction or not as viable as you originally thought. So, these research labs that are actively looking at microscale and doing materials investigations have a very hard, the media is sometimes hard on them because they deliver an improvement at that scale, and it is promising, but the media looks at it as a perspective of, yes, but I can't buy a cell that is better than the one in my phone at the moment. And I think it can be unfair in those senses, and we absolutely need those labs to continue doing that work so that in 5 to 10 years those iterative steps result in a better cell for us to use worldwide.
Yeah, fantastic. Sounds challenging and promising. As a question, what about the mixing of battery and hydrogen? There is a UK pilot train example in the Midlands.
Very cool.
Don't know whether we touched on that, batteries, hydrogen, mixed approach.
We think it'll happen.
Earlier, didn't we? Really?
No, absolutely. I think it most likely will be a viable solution for the heavy duty solutions. There's a lot of really cool work happening in the Midlands, I believe, around hydrogen. And I suspect, we'll see that. Well, what I hope we'll see is that there's less competition and more collaboration between those two fields. Because at the end of the day, they're both still a step change towards a conventional petrol in terms of climate change and
diesel.
Or even diesel.
Yeah.
Fantastic. And then I think probably the last one is, are there any concerns related with minerals for battery applications in the clean energy transition? Maybe related to the previous sort of.
Yeah, exactly.
Dads are absolutely, but you're choosing which devil you deal with.
Yeah, exactly.
Yeah, amazing.
So lots to consider. And then, yeah. So I think I haven't seen any others, and I'd say we've got through quite a few questions there. I think it was thank you very much for a fascinating talk about the activities you're involved in, some of the work that you've undertaken, and the output, and actually the sort of open access to the output. So I'd say thank you to Katie and Brady for a fascinating talk. Thank you to everybody for joining us. I hope you've enjoyed it, and I'm sure Katie and Brady, if you've got other questions, the contact details were on the screen. I'm sure there'd be, if you want to get in touch, I'm sure they'd do their best to interact with you or answer any questions or discuss batteries, etc. further. So yeah, thank you very much. Really appreciate your time. Thanks to everyone for joining us. I'll just stop with the last sort of plug that the 15th of February there is a talk regarding energy and our homes, and in the chat there's a link to book onto that. It'll be a very interesting event. So hope to see you at some more events. Thank you, Katie and Brady, and take care, everyone. Stay safe. Cheers all.
Bye.
Thank you.